Looking back, looking forward, looking down, looking up, looking around. Come, join a journey of exploration to the distant past, to the frontiers of tomorrow. From the infinitely small to the infinitely large, the mysterious, the mundane. Come, let us travel to the horizons of knowledge. This program has been made possible thanks to a generous grant from the Swiss Agency for Development and Cooperation, the Vodafone Egypt Foundation, the OPEC Fund for International Development, and the Carnegie Corporation of New York. Since the earliest times, humans have looked at the heavens and tried to understand the stars, the sun, the moon. They formed images of the universe and of our place in it. Mostly fanciful, these early images of the cosmos became the precursors of our modern cosmology. Gradually, we learned to understand the stars, the structure of the universe, and today we have come to know the true magnitude of the physical universe in which we exist. Its vastness in terms of time and space exceed the wildest dreams of the ancients, and the enormity of the cosmos is really a challenge to the human imagination to fully embrace it. Yet, we believe that we understand it. And this is the story of modern cosmology, of that journey of discovery and understanding of the universe. That is the story of cosmology. The ancient Egyptians, the Mesopotamians, and the Greeks struggled with the images of the cosmos. Most put the Earth at the center of the universe, a geocentric model of the cosmos. But in ancient Alexandria, for the first time, a human being, Aristarchus of Samos, actually proposed a heliocentric model of the cosmos in which the Earth revolved around the sun. Few agreed with him. And in the 2nd century AD, Claudius Ptolemy presented his treatise with the Earth firmly at the center of the universe. His vision would dominate the world for the next 1400 years. Medieval cosmology remained largely dominated by the ideas of Claudius Ptolemy and his massive astronomical treatise, the Almagest. It placed the Earth firmly at the center of the universe. It explained the observed motion of the stars by complex additive motions in their orbits. This astronomical vision, strongly supported by the Church in Europe, was translated into a cosmology that saw the stars as sitting on one or more spheres that surrounded the Earth, itself recognized as a sphere, even if a few extremists considered that the Earth was flat. Now, these spheres rotated in certain ways that explained the observed motion of the stars, created beautiful music that was to be the music of the spheres. In the West, this state of affairs would remain largely stable and unchanged for almost 1400 years. But in the East, Muslim astronomers were questioning the mathematics of Ptolemy and making ever more precise measurements called Zij, from the Great Mosque in Damascus to the magnificence of Abbasid Baghdad, to the emergence of Maragha, to Ulugh Beg's observatory in Samarkand. Muslim astronomers not only named the stars, they also developed ever more sophisticated models and mathematics that took them further afield from the Ptolemaic model. Al-Khwarizmi, Al-Urdi, Al-Tusi, Ibn al-Shatir, and many others were building this great edifice of analytic power and understanding. That task would be done in Europe. As it awakened from the Dark Ages and moved from the Renaissance to the scientific revolution in the 16th and 17th century. Copernicus, Galileo, Kepler, and Newton would forge the revolution that would start modern cosmology as we know it. Their stories are well known, and it was Newton who would finally create the entire edifice of celestial mechanics with his incomparable Principia. There he would lay down the simple rules that govern the universe, from an apple falling to the ground on Earth, to how the moon remained chained to its orbit around the Earth, to the movement of the planets around the sun in an exemplary display of rigorous mathematics and impeccable logic. Newton's orderly world, with its absolute time and three-dimensional space, would remain the model that most of us still operate with to this day. At the start of the 20th century, physics seemed victorious on many fronts. There were a number of small anomalies that bothered the scientists. In 1905, an unknown 26-year-old young man who did not have his doctorate yet, who was not at a university but working at the patent office in Bern, Switzerland, sent 5 revolutionary papers that would change the world forever. The unknown young man was Albert Einstein. Just how revolutionary each of these papers was is almost unimaginable. Time and space were combined into space-time and were no longer absolute. Matter and energy were the same, and E equals mc squared showed that. The statement that you could convert a very, very small amount of matter into an enormous amount of energy was almost totally unbelievable. Yet, 40 years later, we witnessed the atomic bomb. Einstein did not address gravity in 1905, but 10 years later, Einstein would unleash his second revolution, for he incorporated gravity into what became his general theory of relativity. Gravity, he said, was due to distortions in space-time created by massive objects that therefore changed the course of other objects. It was like putting balls onto a sheet and then shooting marbles past them. So the marbles would be deflected because the surface of the sheet would be distorted by the presence of the balls. The theory predicted that light would bend around a massive object such as the sun, and thus stars would appear to be in a different location than we knew them to be. But the sun is so bright that you cannot see the stars next to it, unless there is a total eclipse. And there was such an eclipse in 1919, and Arthur Eddington led an expedition that confirmed Einstein's predictions very precisely. Wow! a new cosmology was born. Newton's world was replaced by Einstein's vision. A complex and weird cosmology was being created. But the Einstein equations predicted an expanding universe. And even the revolutionary Einstein could not easily accept that. And therefore, he introduced a constant called the cosmological constant to make the equations predict a stable universe. Enter Edwin Hubble, the greatest astronomer of the 20th century. Hubble's observations with ever more powerful telescopes convincingly gave us the notion of galaxies and reduced our solar system to an insignificant part of the Milky Way galaxy. Which is itself a minute speck as one galaxy out of a cluster of galaxies that are part of possibly 100 billion galaxies or more in the universe.
But Hubble also did more. He measured the movement of the stars by the shifting in the composition of their light.
The discoveries by Hubble were just unbelievable. It was kind of, his idea was a bombshell, because he told us that the universe is much vaster, much more expansive than we ever thought.
So is the light of stars shifted towards the red if they are moving away from us, and towards the blue-violet if they are moving towards us. Hubble's measurements were a bombshell. His law organizing the measurements was unequivocal. The universe is not only enormously large, but it is also expanding, and stars and galaxies are moving away from us at a very fast rate.
There is so much more that we can learn about the universe, particularly since the universe continues to expand. It's expanding, and we need to expand our mind and our knowledge to know more about it.
Einstein's original equations perhaps did not need a cosmological constant after all. Although we have now returned to the need for a cosmological constant to explain some of the other features of the universe as we understand it at the beginning of the 21st century, still it was a period when suddenly the expanding universe of Hubble was replacing the static universe of Einstein. So how did the universe start expanding? Georges Lemaître, a Belgian priest, postulated that there must have been a moment of creation in the very distant past when it started from a mere speck. But where did all this matter in the universe come from? The advocates of the expanding universe, including Hubble and now a chastened Einstein, agreed with Lemaître. That theory became known as the Big Bang. It postulated that at some moment, from a singularity started the Big Bang that created the matter and energy of the universe. It is the prevailing view to this day.
Evidence for the Big Bang has been found in many ways, but one of the most important is that there should remain some background radiation and heat in the universe that is still there after the postulated 13.7 billion years of the universe's existence. Well, there is.
Here is an image of the background radiation. If the universe was formed by the Big Bang some 13,700,000,000 years ago and has been expanding ever since, just how big is it today? Here I have to use an analogy or a series of analogies. The sun, our sun, is 1,000,000 times the volume of the Earth. Its diameter is 109 times the diameter of the Earth. Now, here I hold an aspirin. small pill is about 1 centimeter across. So to understand the relationship between the stars, if the sun, our sun, were the size of this aspirin, the nearest star would be 140 kilometers away. Now, huge numbers of stars together form a galaxy. Our Milky Way galaxy has several 100 billion stars in a disk. It's really difficult to imagine the size of our galaxy. Now, if the whole Milky Way galaxy was the size of this aspirin, then the nearest galaxy, which would be the Andromeda galaxy, would be 13 centimeters away. So in galaxies, the distances are shorter than between the stars. Both are part of a cluster called the local group. The next nearest cluster would be 60 centimeters away, and some 3 meters away there would be a cluster of 2,500 galaxies in a volume that would be about the size of a basketball. It's called the Virgo cluster. But the universe has several hundreds of billions of galaxies. So if a galaxy, like our galaxy, was the size of this aspirin, how big would the universe be? With several hundreds of billions of galaxies, it would be about 1 kilometer across. Light travels at 300,000 kilometers per second. That is so fast that it seems instantaneous. But light takes time over very large distances, such as those enormous distances in the universe. It takes light 8.3 minutes to travel from the sun to us on Earth, because the distance is 150 million kilometers. Thus, if it takes light some 8 minutes to travel from the sun to us, the image we see of the sun is how the sun was 8 minutes ago, not how it is the instant we are seeing its image. If it takes light 4.37 years to travel from the star Alpha Centauri to us, it follows that when we see Alpha Centauri, when we take a picture of it, we are taking a picture of it as it was 4 years and 4.5 months ago, when the light left it to come to us, and not as it is at the instant the picture is being taken. So the more distant a part of the universe we are looking at, we can see the way it looked a long time ago. We can sort of see into the past and see how things looked billions of years ago, if they are billions of light years away. We cannot do otherwise. We cannot see it instantaneously. And because the Hubble Space Telescope is beyond the atmosphere of the Earth, and it can see farther and more clearly than any other telescope that we have created so far, it actually can see the most distant objects in the universe, and therefore the oldest objects in the universe, those whose light has taken the longest to reach us. And so, as we use Hubble to look further and further away, we can see further back in time, to the formation of gigantic clouds and columns of gases, to the formation of the galaxies, to the formation of the stars, to the explosion and death of stars, supernovas. look at nebulas. And we can keep on going and going and going. We can keep on going to the most distant objects in the universe, almost some 13.7 billion years ago. As close as we can get to seeing the Big Bang itself, at the starting point of creation, at the intersection of physics and cosmology, at the birth of matter and energy, at the start of space and time. But if our view of a huge universe formed from a speck some 13.7 billion years ago seems fairly solid for now, there are some real peculiarities predicted by the equations and that we have begun to have more and more evidence of. And these include black holes. There are cases where the collapse of a star upon itself creates such a dense mass that it starts attracting all other things around it into itself. And the density of that small body becomes so large and its mass so great that even light cannot escape from its pull, and it appears as a black hole. Secondly, we cannot explain what we are witnessing in the universe by our current knowledge of matter and energy. And we therefore believe that about 22% of the universe is something else we cannot see or capture, but that we can deduce by the observed and measured effects, and we call it dark matter. Third, we still need to add another 74% of the universe in terms of dark energy to be able to make our current math and our observations come out correctly. The stars and the intergalactic dust that we can see and measure, therefore, would represent only about 4% of the universe. So there is an enormous amount about the universe that we still do not know. Today, there are more scientists working on these problems with more means at their disposal than the cumulative total of scientists and equipment deployed in the entire history of humanity. We are about to embark on an even larger journey of exploration in our quest to understand the universe and our place in it. It is truly an exciting story, but that is a story for another day. Till we meet again, I am Ismail Serageldin, thanking you for having watched this episode of Horizons.